All right, everybody, this is the exam one review. We will be starting in just 30 seconds after I take off my jacket and I get the screen on. Let me just see. And I need a link. So I just need one more bit of information. Who knows how to get the link? How do you know the link? Help me out here. Somebody know? Come on, you're the Twitch streamer. Get up here. Help me. Look at what you do. Live, but I'm looking for... How do I get to the stream? I'm streaming.
On Twitch?
No, I'm on
YouTube. Got it. Okay, YouTube Gaming. Just copy the link.
No, it just says YouTube webcam.
Oh, that's a webcam. Are you live?
I actually have done this before.
Maybe go
live, maybe here. Maybe it's probably under here. Huh? No. Cancel.
Yeah.
How about here?
Click the little button right here. Maybe.
Yeah.
I don't think the 3D glasses.
Expensive. Sorry.
Yeah, because those are balloon, right?
Hard to see very well.
Hi, everyone. Okay, but I remember there's a way to see your live stream. What's this?
Oh, right here. There.
Yeah.
Oh, this?
Yeah. Let's see. Click that.
Oh, awesome. Thank you so much.
Yeah.
Awesome sauce. Woo! You know what? When things work, don't you feel happy? I just love that. Okay. Turn the screen on. Let's get happy. Let's get this going. Get the show on the road. I'm late. You got at least 2 hours worth of work, right? Actually, I think you can do it. It depends on how much detail you need, though. So if you need a lot of detail, then slow you down a little bit. That maybe will help you more. So it's for you. This is for you. So we do what you need, right? I have a study guide. I want to go over the whole study guide. You don't have to sit. You can sit anywhere you want. No clicker tonight, right? We're just here. So I'll pass around the attendance sheet in just a moment. You may sit anywhere you like. I forgot to bring cookies. Next time I'll bring cookies. So I am planning on doing one of these for every exam. Okay? I'm going to try to do that. That's my hope. And so today is our first one. Yeah, I need to log in. Okay. So I want to just see if the live stream is truly working. Hello. Tommy, can you hear me? Link. Okay, now.
Check my email to see if
It probably did because I made an announcement. Okay, that'd be awesome. Let me just see if I can see the screen. Oh, I see the big Google. I see the Google. Okay, it's a little skew. Are you streaming?
Yep.
Okay.
It's there's a little delay.
Yeah. Okay. Well, I'm gonna just. Okay. All right. We gotta log in. I got 10 seconds. I should have come 5 minutes earlier. But a student came in the last 5 minutes. He's hard work for tonight. Who knows why? Making a start last minute. Okay. I go to my email. I emailed myself all the through. Me. Go to work. Okay. All right, ladies and gentlemen, I want to make sure you understand these are 5 questions that are on your exam. This is the first question. Okay, you might recognize the figure. Okay. The following figure shows Earth orbit around the sun. Which position corresponds to autumn in the southern hemisphere? So in order to answer the question, you need to identify what season is autumn? Well, it's in between summer and winter. So you need to find summer in the southern hemisphere and winter in the southern hemisphere. And then you should be able to identify autumn. It will be the one in between. Okay? So can you understand? So this is the north. And so that would be, this is the south. That would be winter. Which means that this one, the south is facing towards the sun. That's summer. So which one is in between summer and winter? Why is the screen shaking? Earthquake. That was an earthquake. I'm not even kidding. That was an earthquake. Did you not? That was an earthquake. Freaky. Woo! While we were live streaming. Like, that's funny. It wasn't very big, but that was a little earthquake, right? That was the projectors wiggling. That's what was going on right there. Okay, we're okay. Everything's good. Okay, here's summer in the southern hemisphere. Here's winter. Which one is autumn? D, right in the back there. Between summer and winter, you go this way around. This is autumn. This would have been spring, but that's not the question asked. What will the question be? This is the question. This is the question. It's one of your 75 questions, okay? I'm cheating. I'm giving you the answers, right? Everybody got it?
Can you explain that?
One more time?
Can you explain it?
Okay, so the poles of the Earth are here. The top of the Earth is the northern hemisphere. This is summertime in the northern hemisphere. It's winter time in the southern hemisphere because you're facing away from the sun. Over here, we have winter time in the northern hemisphere because we're facing away from the sun, or tilted away from the sun, sorry. And then in the southern hemisphere, it's tilted toward the sun. That's summer. So we go this way around the circle, around the orbit. If this is summer and this is winter, this D is the one in between. We call that autumn. And this would be spring. But we don't need that. We need autumn. Okay, the answer was that D right there. Okay. All right, this is a little tricky. Again, I don't know if you memorized it, but there you go. At what time of the day does the moon rise above the eastern horizon? When it is a first quarter moon. So I actually memorized this. Anybody know the answer? 6 p.m. Oh, wait. No, I'm wrong. Sorry. It's highest at 6 p.m. What time did it rise? It rose at noon. Okay, the first quarter moon rises at noon. It's highest at 6 p.m. and it would set at midnight. But you just need, what time does the first quarter moon rise? The answer is at noon. Questions? You just memorize it. This is all being live streamed and recorded for later. Okay, so you can go look at it later. Question number 3. Okay, this is a new topic which I have not covered in class. Good luck. Just kidding. It's not that hard, but anyway, an astronomer takes a spectrum of a nearby star. Now, just an add-on feature because we talked about it today. What kind of a spectrum would a star be? There are 3 spectrums to talk about: continuous, absorption, or emission. Which one would it be? Absorption spectra. The light from the hot star has to pass through its atmosphere. And in the process, some of the light is absorbed. We'll talk about it tomorrow just before your exam, but it'd be good for you to understand it. So we'll go over it a little bit later in our review. Okay? So that is called an absorption spectrum. But wait, it says that the identified absorption lines all appear at shorter wavelengths. So actually, you need to answer the question, what about the frequency? If the wavelength is shorter, what does it tell you about the frequency? It's a higher frequency. Now I'm going to remind you that there's an effect that I showed you in a little video clip called the Doppler effect. In the Doppler effect, if a source of a wave is coming towards you or going away from you, you do not see the same frequency. So when I was showing you a video of when I was in Italy, driving through the sunflower field. Do you remember how the sound of the horn was when the car was coming towards you? Higher pitched, right? Coming towards you, you hear a higher pitch. Going away from you, you hear a lower pitch. So what happens to light when the star is coming towards us or moving away from us? It is also shifted. So when it's coming towards us, what is it shifted to? A higher frequency. This is called a blue shift. That's what it's called, a blue shift, towards the blue or towards the higher frequency. If the star was moving away from us, what would happen to the light? It would be shifted to a lower frequency. We call that a red shift. Okay? So what's the best answer? An astronomer sees that the absorption lines are all shorter wavelength. You should translate that to higher frequency. And what does it mean? Is the light coming towards us, or is the star coming towards us or moving away from us? Towards us, okay? So she concludes the star is moving toward her, is the right answer. You guys okay with that? Good, okay. Star, we haven't covered this yet either. Okay, don't worry, everything's cool. Maybe today we'll do it right now, huh? Star A and star B have identical luminosity. Does anybody know what that word means? You do know, good. What does it mean?
They are the same brightness.
It's the amount of light coming out of a star per second. I don't know if you remember that. It's the power of a star. I don't know if anybody remembers that. I did mention it. Total amount of light per second that comes out of a star. So two stars have the same luminosity, but star A is twice as far away as star B. So you understand, one of the stars is closer and one of them is further. Which one will be brighter? The closer one or the further one? The closer one will be brighter. The closer the star is, the brighter it is. But you have to learn a special little detail. Now, those of you who can't see my board right now, I'm writing an equation for the brightness of a star. We'll cover this just before the exam tomorrow, but you need to know it. It's in the book as well, obviously. Let's write down the brightness of a star. The brightness of a star. The light of a star shines in every direction. I've actually showed you this as well, but let me just remind you. It's the luminosity, but then the light is shining in every direction. And so every pulse of light that shines away from a star makes a spherical surface. And the light has to spread itself on a larger and larger sphere the further away from the star we are. And so you divide by 4 pi d squared. That's the part that's important for you. What happens when you go further away? When the distance is larger, the brightness goes down. But you can tell me now exactly what happens when you double the distance. What happens? You double the distance, but you have to square the factor of 2. What does the 2 become?
4.
A 4. And so the light of the star that is twice as far, 4 times fainter, right? Oh, sorry, one more time, sorry. Star A is twice as far. So star A will be 4 times fainter than star B, because star A is twice as far, right? Final question. All of these are on the exam. They're going to be verbatim, meaning word for word, exactly the same on the exam. Third, last question. Which of the following colors is emitted most strongly by the sun? Does anybody know the answer? Yes. Oh, that's a good guess, and it's wrong. Yes. Green. 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 Who remembers why green is the right answer? It's in the middle of the spectrum. Roy, G, right? The G is in the middle of the spectrum. It is the light that comes out most strongly from the sun. Again, I should have covered that already. I have not. I will cover it as part of our review. It's called the Blackbody spectrum. All right, everybody understand the first 5 questions? Yeah. All right. If you're ready, let's go through our review. Now, we can go forwards or backwards. Do you want to start at the end and work backwards, or start at the beginning and work forward? Do they have a preference? Beginning. Okay, so the benefit of doing the end is we haven't covered everything in class. So I can actually take time right now and teach you. And that way, even though I'm going to do it tomorrow morning before the exam, you'll already understand it. Do you like that idea? I think it's probably the right thing to do. So we're going to jump down to chapter 4 and do chapter 4 first. Okay? And we're going to do the other chapters as well, but we're going to go back, right? We'll go backwards. So chapter 4, we've got some ideas. Some of these ideas we should know. The first word, spectrograph, is all of the colors of light that come out of something. The spectrograph is a picture showing all of the colors of light. It's called it's another word is the spectrum. So you can think about a rainbow of colors that you saw coming out of the light that we looked at today. The word wavelength, hopefully you're familiar with that. Everybody know what wavelength is? It's the distance over which the wave repeats, right? So it's one complete cycle of the wave. One complete cycle of the wave, the distance of one complete cycle. What is the frequency? The number. What that was? From the center to the top, or from the center to the bottom? It's a wave, right? from the center up peak or from the center down to the bottom. That's the amplitude. So the amplitude is how big the wave is, how far it goes from equilibrium. It's how far away from equilibrium does it get. What about electromagnetic radiation? What are we talking about? Light. Think about light. Is it visible or invisible? Both, right? Everything, all the electromagnetic radiation. The electromagnetic spectrum, that's all of the different kinds of light. Should we name them in order right now? Let's see if we can figure it out. From the lowest frequency, radio waves. Next, before infrared, microwave, right? Radio, microwave. Next one, infrared. All right, now we got the visible one. Remember the colors. Red, orange, yellow, green, blue, indigo, violet. Okay, now we're past the visible. What's next? Ultraviolet. Next, X-ray, and finally, gamma ray. So what's a gamma ray? A very high frequency light, very high frequency. So we learned today that the energy of a particle of light called a photon depends on the what? The wavelength of the frequency. Which one? The frequency, that's the key. So which color of light, visible or invisible, has the highest energy per photon? Gamma rays, right? Because they are the highest frequency. Each one carries the most energy. They're really energetic photons, okay? All right. Refraction is a word that all waves do. Refraction means the bending of light when it passes from one medium to another. Actually, what I can do is, because this is a visual thing, let me just show you with Google Images. I'm going to show you a picture of refraction. Okay, refraction. The rays of light, a laser beam, comes from one medium, travels into another, it changes direction. That's called refraction. Do we ever see light refracted? Have you ever seen it? Well, when it goes from air into water or air into glass, refracted, it also gets refracted by the atmosphere of the Earth, right? It gets bent by different densities of atmosphere. So raise your hand, you've seen a star twinkle. Why is it twinkling? The light is getting refracted, and different colors get refracted different amounts. The stars twinkle. It's the turbulence in the atmosphere that's giving us this effect, okay? So that's why it's relevant to you. What about the word spectrum? Oh, spectrum is a spectrograph. Spectrum and spectrograph are kind of the same thing. It's all of the colors of light that are present in some light source. Okay? So whether it's white light or some other colored light, it's the colors that are present. I'm going to show you some pictures in just a moment. Okay, kinetic energy. Do you know what that means? Kinetic energy? The energy of a particle that is moving. Now, mostly, we know it's in physics, but if I said, what's the formula for kinetic energy? The formula is, it's not there. There it is. K, 1/2 mv squared. 1/2 mv squared. Who knows what m stands for? Mass. Mass. You've got to have mass to have kinetic energy. What does V stand for? Velocity. We've got to have velocity to have kinetic energy. Any object with mass and velocity has kinetic energy. So the other kind of energy that we talk about is called gravitational potential energy. That's the next term, gravitational potential energy. So the way that I describe that is actually when we're near, okay, so potential energy is sometimes called stored energy. And I could kind of leave this out, but let's talk about it right now. Gravitational energy is the idea that if I lift my keys, they have more energy than when they started. How do I know that? Well, when I let them go, what happens? They start moving. What kind of energy do they have? That's called kinetic energy now, right? They have kinetic energy. They didn't have that kinetic energy before. So actually, I don't see the term up here, but can I mention it out loud? There's an idea that's pretty powerful in science called conservation of energy. Energy cannot be created or destroyed, only transformed from one kind to another. It's a pretty big deal, okay? So what happens is when I lift the keys, I give them this kind of energy called potential energy. And when they fall, it turns into what kind of energy? When they fall, it turns into kinetic energy. But the total amount of energy is remaining the same, right, after I let them go. So when I lift them, I'm actually giving some of my energy to the keys. Yeah.
So when I move my bike on the hill, I have potential energy.
Yes.
And when I go down.
Yes, you go faster, you have more kinetic. But yeah, okay. So the reason this is interesting is we talked today just briefly about the concept of escape velocity, right? What's escape velocity? It's how fast you need to go to leave the Earth. So I'm just going to show you just quickly how this works. If I lift my keys, am I gaining potential energy or losing potential energy? What do you think? I'm gaining, right? The further they fall, the faster they're moving when they hit the ground, right? The higher I lift them, the faster they will be moving when they hit the ground. That's called kinetic energy. So the higher I lift them, the more potential energy they will have. Well, what's the furthest I can lift them? Well, very, very far away. We say infinity. Are you okay with that? So I could lift them to infinity. I can't really do that. So what's the deal? When they fall, do they gain or lose potential energy? They lose, right? They lose potential energy. So it's kind of an interesting idea. Wow, I'm really going off topic, but let's stay targeted. When I lift something, it gains potential energy. When it falls, it loses potential energy. The furthest I can take it is to infinity. I can't really do that. So let's say I do. Just pretend. How much potential energy does something have if I take it infinitely far away from the Earth? The answer is 0. That's weird. And I'm sorry about that. But just stay with me, right? If you go to infinity, it's 0. What happens when you fall closer to the Earth? Does the potential energy get bigger or smaller? Well, it gets smaller the closer I get to the Earth, right? Remember, when it falls, it lowers the potential energy. So when it's at infinity, it's 0. What's below 0? Negative numbers. So when something is on Earth, it has what is a negative energy. It's called negative potential energy. Anything that's stuck on the Earth has negative energy. If you want to leave the Earth, you need to have 0 or above energy. What kind of energy do you need to leave the Earth? Kinetic energy. So you get enough kinetic energy, you can get away. If you don't have enough kinetic energy, you can't get away. So anyway, don't worry too much about this. You don't need to know a lot about this. So we talked about the escape velocity is the speed needed to get away from a planet or object. Okay, and I'll talk to you in a few minutes about what kind of things you need to know. Okay, you can have more mass or less mass, or bigger radius or smaller radius, and then we can answer the question. Okay. What's thermal energy? The energy of a hot object. Hot objects have thermal energy. Okay, now this is actually what I was hoping I was going to get to today. It's a topic called blackbody radiation. Every object with a temperature above 0 radiates energy, including you. We have a beautiful little demo I'm going to do. I'm going to go to one of my favorite websites, PHET simulation, black body, okay? And then I'm going to go click, and I'm going to go click, and it works. Okay, beautiful. So there's a couple of things I'd like to highlight on this. Let's see if I can turn off the lights. Can you still see? Oh, beautiful. Let's keep it better. Right there, that little picture right there is the color of the star. What color do you see? What color? Blue, green, red. Whitish, yellowish, I don't know, orangish, I don't know. It's not really bright white or something, right? It's not bright white. But you'll notice that the temperature is not quite right. Now, does everybody see with the big K, that big K right there? The temperature is measured in K. What does K stand for? Called Kelvin. So I don't know that we have a lot of time to talk about this, but you have to use Kelvin. And Kelvin is special. It's something that has no negative numbers. There's no negative Kelvin. There's negative degrees C, and there's negative degrees Fahrenheit, but it turns out to get this right, you have to have a temperature scale that never goes negative. What is the lowest temperature that you can reach in the Kelvin scale? 0. And it's called absolute zero. Right? Do you want to write that down? That's probably an important idea. If something gets to absolute zero, then it has no motion at all. Good question, I'm sorry. Yes. Oh, absolute zero. There's no motion at all. No kinetic energy at all. So thermal energy is actually a kind of kinetic energy. Did you hear that? Thermal energy is the kinetic energy of the individual atoms or molecules. It's a kind of kinetic energy. Okay? So thermal energy, that motion of the particles, is a kind of kinetic energy. All right. So I want to show you two things. This is called the Blackbody spectrum. Is it symmetric or not? No, it's not symmetric. Is that a big deal? Not a big deal. This is actually, for a more advanced course, it would be a big deal, but for us, it's no big deal. Just notice it, okay? I want you to notice right here, this is wavelength getting longer, right? Wavelength getting longer. So you can see that that's right, because what's the longest wavelength light that we can see? The red, and the shortest is violet, right? See how it works? Shorter wavelength, 400 nanometers, red, 700 nanometers. Remember the range of wavelength, okay? Now, there's two ideas. Number one, there's a place where the light is highest. That's called the peak. This particular shape here is actually coming from a couple of different equations, which we're not going to study too much, but you want to understand two things. Number one, the location of the peak depends on the temperature, number one. And the size of the peak also depends on the temperature. Okay? So you want to know how, right? You want to know how does the peak location and how does the peak size depend on the temperature. Everybody good? Those are the two things you need. Okay, I'm going to cover a lot of stuff. I want to raise the temperature now. I want you to watch what happens. So where is the peak right now? On the yellow. It's about yellow right now. Okay, the peak. So here I am. I'm raising the temperature. And about 5,700 Kelvin is the temperature. So you could write that down if you don't know it. The temperature of the surface of the sun is about almost 6,000 Kelvin, 5,700 if you want to be precise. I want you to look at the star. It looks pretty white right now. You see it's pretty white. But you want to understand that that's because it has all the colors of the rainbow mixed in. So when we mix all the colors of the rainbow, we see white light. White light is everything, all of the colors mixed in. So today when I turned up the bulb, did you see all the colors mixed in? They were all there, but the light was a very white color, okay, very bright. Now, what happened to the location of the peak? When I made it hotter, which way did it go? To this direction or this direction? It went this way. To longer wavelength or shorter wavelength? Raising the temperature, what did it do to the wavelength, the peak wavelength? Made it shorter, right? So it goes to a shorter wavelength, which means what about the frequency? Higher frequency. Raising the temperature means that the peak will have a shorter wavelength or higher frequency, right? Okay, now what if there's a star that's hotter than our sun? Is there such a thing? Oh yeah, there are. Of course, our sun is not that hot, right? It's beautiful, but not that hot. Okay. You'll notice that I made it really hot, as hot as I could go. And where's the peak? I can't even see it. Oh man, I failed. Oh, I did it. I'm gonna fix it. I want you to notice, first of all, the color. What do you see? What color is that star? Blue. Blue, write it down. Blue stars are really hot stars, right? This is awesome. Why is it blue? Why is it blue? Okay, so let me shrink it so that I can see the whole thing. Who can explain why it's blue?
High frequency.
Okay, but what does it have more of? More of the violet and blue or more of the red and the orange? But as you can see, it's going swooping down. What does it have more of? More of the blue and the violet. Less of the red and the orange. What does it look like? Blue, right? Where is the peak located? What color is the peak?
Ultraviolet.
Ultraviolet. Very good. You see, it's above violet. It's ultraviolet. So what kind of light does it put out more than anything else? Ultraviolet. How does it look to our eye? It looks blue because there's more blue light and less of the red light. The spectrum has changed. Are you with me? The kinds of colors of light have changed, and so we see something different. Now, it turns out there's a lot more cool stars than there are hot stars. A lot more. So, in fact, you'll learn exactly how many. Let me turn it way down to like 3,000 Kelvin. That's typical. What happened to my peak? Okay, so real quickly, what happens when you lower the temperature?
Lowers the intensity.
It lowers the intensity. Man, it went crazy. Look at that. I can't even see it. What? It's crazy. Okay, so there's two factors: the size of the peak and the location of the peak, right? What happens to the size of the peak when you raise the temperature? Peak gets bigger. When you lower the temperature, the peak gets smaller. In fact, it's so small I can't even see it yet. But I'm going to blow it up so we can see it. And look at the color, by the way. Kind of orange, right? Okay, where's the peak? What color is the peak in?
Infrared.
In the infrared. The peak is in the infrared. What does it have more of? More of the red and the orange, less of the blue and the violet. You guys see it? The stars change color. Okay? So the spectrum that you see is changing depending on the temperature. So temperature changes the peak location and the size of the peak. And do you need to know much more? You only need one more little detail. So number one, where does the peak location go? Hotter shifts to smaller frequency, smaller wavelength, higher frequency. Cooler, longer wavelength, lower frequency. What happens to the size? Hotter, it gets bigger. Cooler, it gets smaller. But actually, I'm going to ask you to know just a little tiny bit more detail. Okay? And the detail is, it's called the Stefan Boltzmann. Okay, it's going to be on the list in a second. I don't like it like that. Can I just write it down? That's pretty good. Okay. Oh, this is ugly. Okay. Your mother loves you. But all right, here we go. P is actually the luminosity of a star. This is really complicated looking. Don't get confused. There's only two things that you have to worry about. When the star is radiating light, what are the two factors that are most important? The first letter is A. A stands for the surface area. The surface area. Every square meter of the star is emitting light. So the larger the star, the more area it has. The formula for the surface area is 4 pi r squared. We wrote it down a couple of times before. And then the other one is T, capital T. Who knows what that stands for? The temperature. And what power is it? To the 4th power, okay? So you need to know that the two factors involving the luminosity of a star are, the luminosity is proportional to the area times the temperature to the 4th power. You don't really have to use this formula, but you have to get the idea. When you change the temperature, what happens? You change the luminosity a lot, right? What happens if you double the temperature? You got to do 2 times 2 times 2 times 2. What happens to the luminosity? The luminosity is going to be times 16, right? You made the temperature twice as big. The amount of light that comes out of that star is 16 times as much, okay? And then what happens if you double the size, double the radius of a star? What happens to the area? That's the kind of thing that you have to be able to do. The area is 4 pi r squared. You don't care about the 4 pi, just the r. What happens if you double the size of a star? What happens to the area? 4 times as much area. Okay? So those are a couple of the ideas. All right. I realize we're kind of scattered a little bit, but let's go back for a second, guys. Okay, so Wien's law, a photon, we know what a photon is? What's a photon? Okay, it has energy according and is proportional to the frequency, right? Frequency is the key to the energy of a photon. So Wien's law says that the location of the peak depends on the temperature. The wavelength of the peak is inversely proportional to the temperature. You don't actually need that law. You just need to know qualitatively what happened. As you raise the temperature, where does the peak go? Shorter or longer wavelength? Raise the temperature. Shorter wavelength, higher frequency. As you lower the temperature, it goes to longer wavelength and smaller frequency. Everybody get that? That's Wien's law. You don't need a formula. Just which way does the peak go? Raise the temperature, it gets hotter, then you shift it towards the smaller wavelength, higher frequency. Cooler, you shift it to the longer wavelength, smaller frequency. That's Wien's law. Stefan Boltzmann, I wrote it over there for you, said that the two factors that affect the amount of light coming out of a star are the area or the size of the star and the temperature of the star. Those are the two factors. Okay, luminosity, what's that? We just said it a few minutes ago. The total light coming out of a star per second, right? It's the power of a star. Nebula, oh gosh, nebula, what's a nebula? Glowing gases, nebula, glowing gases, not a star, but just glowing gases out there in space, okay? A nebula. Actually, we will talk a little bit more about that. Should I talk about it right now? Maybe I should. Okay, so let's say that star light is shining on a big patch of gas that's just sitting in space, minding its own business, right? What will happen to the light after passing through the gas? Anybody remember? Some of the light will be absorbed, right? You'll lose some of the colors. What it does is it gets the gas excited. Okay, we're going to talk about that in just a moment. And so if you look at a different direction, all of the colors that were absorbed are actually being shot out, emitted by that gas. So the nebula glows with those colors, right? So the light coming in gets absorbed by the gas, but actually shines in all directions. So even if we're not looking at the star that got the gas excited, we can see the gases glowing, and we call it a nebula, right? A nebula is glowing gas. Okay, quantum mechanics. I better talk about this now. Quantum mechanics is the idea that there is a concept called the quanta, that energy comes in small packages, like a photon. That's an example. Energy comes in small packages. And the atom is made up of two parts. One part is called the nucleus. Anybody know this already? Nobody? Okay. A few of you know this, okay? You have the core of an atom, which is called the nucleus. And the nucleus contains two kinds of particles. What kinds of particles? You know what they are. Protons, which are positive. You should know that. Well, the electrons are in around here. They're somehow. And we are going to discuss just a very basic model of an atom. And the model goes like this. The electrons have to be in certain levels around the nucleus. We call these quantum levels. And again, we're gonna go kind of quickly, so don't get too confused. The level that is closest to the nucleus is called level 1. Level 1 is the level closest to the nucleus. I'll show you a graphic in just a moment, online streamers. Anybody streaming? Oh, there's comments. Ooh. Hello. Yes, I did. I went over the 5 questions. But you can look at the recorded stream later, and then you'll be able to see the questions. Would you mind sending them to me? Yes, I would. Sorry. Bye. Okay, look at the recording later. You'll see them. Okay, all right. All right, so the first level is called n equal 1. Has another name you should know. It's called the ground state. Okay, the ground state. A little bit further out, away from the nucleus, higher potential energy, but we don't need to know that. Right? Same idea. Moving away from the nucleus is hard, right? We don't want to go that way. And so we call it level 2. Level 2. And a little bit further, level 3. Are you getting the idea? Okay, so I'm not going to draw any more circles. What I'm going to do is I'm going to jump to the other side of the board and draw a quick little picture called an energy diagram. So the lowest level that the electron can be in is level number 1. The lowest level is level number 1. It's a certain amount of energy. And the next level up is level 2. And the next level up is level 3. And the next level up is level 4. You notice something happening. What's happening to the spacing? It's getting closer together. And again, we're not studying why or anything like that. Just know that that's true. The spacing is getting closer together. So the electrons normally want to be in the lowest level they can be. For a hydrogen atom, the electrons will normally be right here, level 1. Okay? But the idea in quantum mechanics is the electron can only be on these levels. Every element on the periodic table has a unique set of these levels. Every element is different. And what happens is the electron can jump between these levels. How does the electron jump? By gaining energy or by losing energy? That's it. Gain or lose, right? If you go up, did you have to gain or lose? If you go up higher, you gain energy, right? The electron has to gain energy. Where does the electron get the energy from? From light passing through. So remember that the gases get excited. It's actually the electrons that are getting excited. When a photon passes through that has just the right amount of energy, the electron can jump to a higher level. As a matter of fact, if the energy is just this much, it will jump to the level 2. What if it's a little bit smaller? Then it won't touch that photon. It's not interested in any photon unless that photon exactly makes it jump to another level. Yes?
I may have lost myself. Did you say electrons want to be at the lowest level?
They normally want to be there, yeah.
So what would make them want to jump up?
When a photon comes along, and that photon has a little bit of energy that actually allows them to absorb it, then they will jump. So I want you to notice something. What energy does the electron want? Well, it wants this one, but it also wants this one, and it also wants this one, and it also wants this one. There's 4 different colors of light that it wants. This is the reason that certain colors are absorbed by the gas. The electrons can absorb that color. It can only absorb the right color that makes it jump. It cannot touch the colors that are in between. It can only jump between the levels. So how does the electron jump higher? By absorbing a photon. A single photon makes it jump to a higher level. The electron doesn't want to stay there for long though. What will happen eventually to the electron? It'll fall back down to the first state. And when it falls down, does it gain or lose energy? It loses energy, and the way that it loses energy is by emitting a photon of light. So the little glowing tubes that I showed you earlier were getting excited, and what happens is the electrons fall down and they emit light. So one more time, electrons jump between these energy levels inside of the atom. If they jump higher, how does that happen? They absorb a photon of energy and they jump higher. How do they jump lower? They have to emit a photon of energy. So the gas emits light as a result of that. Okay, so nucleus, proton. What's a proton? Positively charged particle found in the nucleus. What's a neutron? A zero charge particle found in the nucleus. Actually, the mass of an atom is in the protons and the neutrons. I don't think you need that yet, but you will. Okay, electrons are little tiny particles that are found outside the nucleus. The Bohr model is what I just explained to you, that the electron can jump between the energy levels. So let me show you a little bit. What's the ground state? When the electron is in the lowest levels. Okay, when the electron is in level number 1, that's called the ground state. But the electron can be in one of the other levels, that's called an excited state. Okay. Emission, what's emission mean? The photon goes in or the photon comes out? Photon comes out, it's emitted. Emission means the light is coming out. Absorption means the photon is absorbed, take it in. Okay, energy levels, that's these things right here. A transition is a jump between the energy levels. So there's going to be a question. I'll give you a question, a rough idea how this works. Which transition produces a higher energy photon? When you go from 5 to 1 or from 3 to 1, which one gives you a higher energy photon? Emits a higher energy photon. 5 to 1 is a bigger jump in energy. The photon will have more energy. It will be a higher frequency photon. So the different jump distances in energy correspond to different energy photons that come out.
Yeah, say about 5 times squared.
No, it doesn't quite work like that. Remember, the spacing is not uniform. But if it was, that would have been right. Yeah, that's true. Okay, Doppler effect. Doppler effect. We just referred to it a few minutes ago, right? Going towards you or going away from you. Doppler effect. What happens to the frequency? When the source is coming towards you, you see a higher frequency. It could be sound or it could be light. It's also called with light a blue shift. So when the source of the light is coming towards you, you see the color shifted towards a higher frequency. It's called the blue shift. When you see the source moving away from you, it will be shifted to a lower frequency called a red shift. I think those words are coming out. Yeah, there they are. Red shift, blue shift, right? What's red shift mean? Higher or lower frequency? Lower. Lower frequency. What does it mean about the object moving towards you or away from you? Far away. Moving away from you, not far away. Moving away, just moving away. You can be close or far, it's not important. What's important is moving towards you or moving away from you. Okay, that's the key. Inverse square law for light. Okay, what does that mean? It's over there. It says that as you go twice as far, the light has to spread on 4 times as big of an area. So the light gets decreased by a factor of 4, right? So every time as you go further away, the light gets dimmer, right? The brightness goes down. But the formula is L over 4 pi d squared, right? So what happens if you go 5 times as far, right? Then you have to put 5d, and then you have to square it. What happens to the factor of the 5? Yeah, it becomes 25. The brightness of that will be 1/25. Okay, so I don't want to do this, but you guys are coming to review. I should give you a little heads up, right? Let me do this. Why not? I want to talk a little bit about light bulbs, right? Which one's brighter, a 100-watt bulb or a 25-watt bulb? Okay, if you're holding them the same distance, that's true. But what happens if you take the 25-watt bulb and you move it really close to you? It could be brighter than the 100-watt, right? Or the other way around, take the 100-watt, move it really far, right? It could look dimmer than a 25-watt bulb. You understand that? Okay, so I want to ask you the question, how does a 100-watt bulb look like a 25-watt bulb? By the way, when I say 25-watt or 100-watt, that's like luminosity. That's what it is. It's the power of the bulb. So I got 100 watts. Okay, 100 watts? Yes?
Double the distance?
Yes, very good. Thank you. You got it so fast. Good for you. Okay, so let me slow it down just a little bit. Okay? Okay, so I'm going to take my 25-watt bulb and I'm going to put it here. 25 watt. Okay, I'm going to put it 1 meter from my eye, right? Here's my eye. And 1 meter from the eye is 25-watt bulb. How does it look like? Well, a 25-watt bulb, right? But what happens if I take that 100-watt bulb and I go twice as far, right? It's not 1 meter, it's 2 meters away from my eye. It's twice as far, right? So if I go up here to the formula, when I put a 2 in here, what are you supposed to do to the 2? Square it, which means you divide by 2 squared. What's 2 squared? 4, right? So even though it's a 100-watt bulb, I'm going to go twice as far, which means divided by 4, which ends up meaning it looks like what? A 25-watt bulb. A 25-watt bulb 1 meter from my eye will look the same brightness as a 100-watt bulb held 2 meters from my eye. That's weird, but you got to get the idea. This is why it's confusing in astronomy. When we see two stars, one is brighter than the other. Do we say automatically, well, that star is a brighter star, right? No, we don't know that. Because there's two ways that a star can be bright. It could be close, or it could be a really bright star, put out a lot of light. So anyways, that was something we'll have to figure out later. All right. Aperture, okay, now we're talking telescopes. So telescope, what's the aperture? The opening that lets the light through. So a general rule of thumb, if you want to build a telescope, bigger can be better, but not always, right? So when is a bigger something better? And the answer is with aperture. The size of the telescope means it can collect more light. So a telescope is like a light funnel. Let me get a picture of a telescope. Okay, actually I've got some other, I need to look at that. Let me put the word aperture. Aperture. Okay. So it's the size of the opening. Okay. The size of the opening. That's complicated. I don't know. Super easy. This is the size of the opening. Did you just get that? The size of the opening. Okay. So does anybody notice the shape? What's the shape? A circle. Okay. How is the size of the opening changing if you change the size? Right. And the answer is the area of the opening. So you need to know the formula is similar. It's not quite the same, but it's very similar. Does anybody know the area of a circle? Pi r squared. You can ignore the pi, but you got to remember the r squared. What happens if you double the size of the opening? What happens to the area? 4 times as much light comes through, right? So when you make a telescope bigger aperture, you get more light. How much better is a 10 meter telescope than a 1 meter telescope? How much better at gathering light is that? 10 meters versus 1 meter. 10 times as big. So what's the answer? 100 times as much light comes into a 10 meter telescope as a 1 meter telescope, right? Bigger is better. Bigger is better. The bigger the telescope, aperture, the better. Okay? So we want light because what we're going to be looking at is things that are far away, right? So the aperture, the angular resolution. Okay. So this is a very tiny little detail, but it turns out that there's 2 factors that affect the ability to focus the light. And you would have to be in a more advanced class to worry about this too much. Just get the idea. It turns out that the 2 factors are, for the angular resolution, are the size of the opening, the aperture size, and the wavelength of the light. And so the formula is, actually I'll just put that on the screen here for the people at home. Angular resolution. It's the size of the opening divided by the wavelength. It's like that, angular resolution. Lambda, oh, I did it backwards. I'm sorry, I did it backwards. I did it wrong. Right, upside down. The angular resolution, the size of the resolution, lambda over d. Sorry, backwards. Thank you, of course, I would have figured that out. So what happens? The larger the size of the opening, the smaller the resolution will be. You'll see more detail. Depends on these 2 factors. Don't worry about the 1.20. That's the size of the opening. Whatever. Don't worry. The lambda and the d are the 2 things. So bigger telescopes can resolve tinier little detail, but it turns out the wavelength also matters. So which color is better at resolving? Red or violet? Which one is better? Violet. The shorter the wavelength of light, the better your detail will be. So red will be fuzzier, and violet will be sharper, right? But it turns out the wavelength of the light that you use affects your ability to focus the picture, right? To get a detailed image. Right? But you don't have to know anything more. This is the basic thing. All right, refracting telescope. What's a refracting telescope? It has what kinds of elements? Things that bend light. What's a refracting telescope? It has lenses in it. Okay? This is a traditional, Galileo's telescope was a refracting telescope. It has lenses, images. Refracting telescope. It has images. It has lenses. So a big lens in the front, called the primary lens for the objective. The objective. And the second one's or plastic, right? The refracting telescope has lenses in it. The other kind of telescope is called a reflecting telescope. What's a reflecting telescope? What does it have? It has a big mirror, right? It collects the light in a big mirror. It's a reflecting telescope. Reflecting. Okay, so it uses a big mirror. Okay, the first thing called the primary mirror collects the light, right? That gathers the light. That's it. Big deal, right? Got a big mirror. So which ones are the biggest telescopes today? Refractors or reflectors? Reflecting telescopes. Turns out they end up being much cheaper and lighter and easier to build. So the largest telescopes in the world today are reflecting telescopes. Reflecting telescope. It's easier to make a really big mirror than it is to make a big lens. Okay? That's the idea. All right. Eyepiece is the piece that you look through. Magnification is the how big the image appears, right? I don't know, why did I have that on there? Magnification, that's all. Just how do you magnify it, right? They talk about it a little bit with Galileo and stuff like that. Let me kind of skip over. Magnification. There's actually a formula, but I don't really want to do it. I skip it. You won't need it. Chromatic aberration. Okay? Different colors bend slightly differently when they pass through lenses. And so as a result, perfectly. So one color focuses, but not every color focuses when they pass through a lens. We call it chromatic aberration. Reflecting telescopes are much better. They don't have chromatic aberration. So that's one of the improvements that you get from using a reflecting telescope. Which one? Chromatic aberration. Oh, okay. Chromatic aberration? That's what we're talking about. Chromatic aberration. Oh, sorry. The colors do not all focus the same amount in the same place because the refracting of light changes depending on the color. So some colors refract more than others.
For this one, I'm looking at how we got two. So is it like, do we do 25 or 25 million 145? So it's d squared equals 4 and 5d?
No. I already said, I'm going to tell you that if you take that 100-watt bulb and you put it twice as far, then in this formula, it's the D that's changing. You have to divide by the 2, right? 2, but it's squared. So even though the luminosity or the power is 100,
Wait, what are you asking questions? Are you going to ask us like what is the same?
right? Maybe that would be the question.
So
How do I get 25? Yeah. How do I turn 100 into 25? Divide by 4, right? So how do you divide by 4? Well, dividing by 4 means I have to make the distance bigger or smaller. You want 100 to look like 25. What do? Make it go further away. So you have to go further. So how do you get a 4 down here? You multiply this by 2, and when you square it, it becomes a 4. So there are many questions like this. It's just and again, we're going to cover it again when we talk about stars. But the further away it is, the dimmer the light will be. And so whatever, it doesn't matter what this is. The most important thing is, if you go twice as far, then what happens to the original brightness? It decreases by a factor of 4. Right? That's the key. That's the most important thing. If you get that, then the other part is just a little detail. It's just more like for a physics class. Don't worry too much about it. Okay. Chromatic aberration, atmospheric transmission. Okay. big deal. Okay, maybe I should just bring up the slides. Now that I think about it, because you guys didn't see all these slides. Should I just do that? Is that okay? Because then the pictures are right here. So, let me bring up that pictures. And some of this stuff is already here. Oh, look at that. Or Adam, to look at the slides right here. I'll try to cover these tomorrow. Doppler effect. Okay. And telescopes, right? Connected telescope. Reflection refractor. Here we go. So when we look at the light from the sun, or from anything, sorry. When we look at the light has to pass from a star or from the sun. It first has to pass through the atmosphere of the Earth, right? Do all colors pass through the atmosphere of the Earth? No. The atmosphere blocks some colors and lets other colors through. Does visible light come through the atmosphere of the Earth? Yes. Sure, that allows us to see, right? You can see stars. You can see the sun. Visible light passes through the atmosphere of the Earth. Good, great. Is there any other color light that comes through the atmosphere of the Earth? Well, it turns out, mostly no. Almost everything gets blocked. Second, there's another big part that doesn't get blocked. Radio waves. So the two light that pass through the atmosphere undisturbed are visible light and radio waves. So what does it mean? You can have a telescope on the ground looking at visible light and at radio waves, and it'll work because the atmosphere doesn't block the light. But what about an ultraviolet telescope? Would that work on the surface of the Earth? No, because the atmosphere absorbs ultraviolet light. Okay, so you can't do it. So where do you put an ultraviolet telescope if you want to make it work? You fly it up into the upper atmosphere, or you put it in space outside the atmosphere of the Earth. Okay, so did I answer your question? What was your question? Wait, what, the white light?
Ultraviolet light.
Oh, ultraviolet light? Yeah, so a little tiny bit makes it through. Most of the ultraviolet is absorbed. Actually, I think I need you to know a couple of little details. You want to learn just a couple of little details. We have different elements. Actually, we're going to study this more. Never mind. You don't need it now. Never mind. You don't need it now. There are different gases in our atmosphere that absorb different amounts. Have you heard of ozone? What does ozone absorb? You know? Ultraviolet. Hence the problem. If there's an ozone hole, what happens? There's more ultraviolet causing more cancer on Earth. Do you want that? No, we don't want that. So when we found out that we were damaging the ozone layer of the atmosphere, scientists were able to convince the politicians to make it illegal to emit those gases into the atmosphere. They're called CFCs. And thankfully, they stopped it in time. And actually, the ozone hole has been healing, although we just discovered that somebody in China is releasing them into the atmosphere. Okay, so they need to stop immediately because they're causing damage. But anyways, mostly it's okay. It seems to be healing. I think by 2030, they're hoping that it's not going to have a hole anymore, which is kind of cool. That was based in the work done in the 1960s. Okay, then other parts of the atmosphere absorb different kinds. The water in the atmosphere absorbs infrared light. So you can't do infrared astronomy on the ground very effectively. There's a little tiny window where you can, but basically you can't. Most of it you can't. Other parts, what else? Those are the big ones. That's good. Okay. So radio astronomy typically is done with not a single telescope, but a whole bunch of telescopes in a big array. And the reason it works is they're connected to each other electronically. Okay? So the reason why they do that is that the separate telescopes connected to each other electronically act like a single big telescope. They act like a single big telescope. So you can do something, a really cool trick. You have an area where you want to put telescopes, radio telescopes, and you put a line of telescopes here, and a line of telescopes here, a line of telescopes here, and it acts like a single big telescope this big. Pretty clever, right? It's called a very large array. It's called a telescope array. I think I have it Very large, VLPA, very large telescope array. I don't have it, never mind. Another thing, so opacity, so let's go through. What colors make it through the atmosphere? We said visible light and radio waves. Everything else is pretty much blocked. So the word transmission means the light comes through. The word opaque or opacity means that the light is being blocked. So what kind of light is being blocked? Opacity refers to the blocking of light. Well, everything else, X-ray, gamma rays, ultraviolets, infrared, not radio waves.
Blocking of light?
Yeah, opacity is the blocking of light. So if it's not transmitted, then it's being blocked. Okay. Adaptive optics is a pretty cool thing. Nowadays, modern telescopes change the shape of their mirrors. And they do this to compensate for turbulence of the atmosphere. It's very clever. Interferometry, can I just get that a little confusing? I put it on the thing now. Okay, interferometry is the idea actually that you complicated. Okay, interferometry means that you. Why do I have it in there? That's complicated.
Is it going to be on the test?
I don't think it's even on the test. I think it's in the chapter. Okay. So all right, how about this? Somebody talked about other kinds of waves, gravitational waves. Gravitational waves are detected by a technique called laser interferometry. It's the word LIGO, the laser interferometry gravitational observatory is how they actually detect it. So they use lasers shining in different directions. The laser beams overlap with each other, and they do something called interfere. And so interferometry is the overlapping of light waves to produce. How does the photon energy relate to the frequency and the wavelength? Higher energy means what? Higher energy. There's the frequency. What about wavelength? Shorter wavelength. Okay. Describe the type of spectrum that results from each of Kirchhoff's three laws. So one is called continuous. What do you get continuous from? Color. A hot body. Any hot body, right? The hot body emits all of the colors in a range of colors. The colors will not be the same every time, but will shift one way or the other depending on the what? The temperature. The temperature. The colors come in a little packet, a spectrum, and the spectrum shifts one way or the other depending on the temperature. Remember how we shift it? Higher temperature, which way does it shift? The peak. Towards the higher frequency, shorter wavelength. Lower temperature, it shifts to the lower frequency, longer wavelength, right? The peak shifts one way or the other. So the colors that we see will change. And then the size of the peak will change as well, okay? And what's the other ones? When the light travels through a gas cloud from a continuous spectrum through the gas cloud, what do you see? It's called the absorption spectrum. You lose some of the colors to the gases, right? But if you look from the side, you can see that the gas will be emitting light. It's called an emission spectrum, right? And it looks like the lines of color that were exactly the ones that were subtracted in the absorption spectrum. That's not a coincidence, that's why, right? The light that was absorbed then gets re-emitted again, okay? All right, describe, I just did this, okay. So describe how the black body spectrum is affected by temperature. Using Wien's law, that's just the location of the peak. The higher the temperature, the shorter the wavelength, higher the frequency of the peak. What happens to the size of the peak as the temperature goes up? It gets bigger. Higher the temperature, bigger. Well, how does it get bigger? Temperature to the 4th power. So if you double the temperature, we said 2 times 2 times 2 times 2, 16 times as much light comes out. That's a lot more, right? Want to go one more step? What if you triple the temperature? Anybody do that in your head? 3 times 3 times 3 times 3. 81 times as much light comes out. Okay, just to get the idea, it's huge, right? Huge. Temperature makes a big difference in the light that comes out. Okay, describe how an electron can jump higher or fall lower in an atom. How does that happen? How do electrons jump higher? It's through absorbing a photon, right? It can jump higher. Has to be the right amount of energy, though. It will not touch photons that don't have exactly the right amount of energy, which is why most of the colors go through and are undisturbed. Only the certain colors that are the right colors. How does an electron fall lower? What has to happen? It has to emit a photon and make that jump. It loses that energy, it emits a photon of that energy. Explain how the light of a star changes with respect to distance. So the further away from the star, what happens? The dimmer the brightness will be. How? Well, it's divided by 4 pi d squared. It's called an inverse square law. Gravity does it, light does it, lots of stuff does it, okay? So you want to know that idea. The further away you are, the dimmer it is. If you go 10 times as far from the star, what happens? Brighter or dimmer? Dimmer. How much dimmer? 1/100th of what it was originally, right? The further you go, the dimmer the star. Yeah. No, we don't do those calculations. It's just comparison. Yeah, comparison. The only thing that I showed you was that idea with gravity, which we'll go over in a little bit, where you might have to figure out a number. But I gave you the first number, and then you just have to figure out if I doubled it, what had to happen. If the distance doubled, then gravity was 1/4 as big. Right?
So
That
we
kind of
don't need to know.
thing. Yeah, you don't need to know. Yeah, I don't think I'd be doing much of that. Okay, let's see. Describe how the angular resolution depends on the wavelength. I think we did that already, right? The shorter the wavelength, the more detail you see. But what's another way to get better detail? Larger aperture. The larger the telescope, the greater the detail will be. This is why the Hubble looks so amazing, right? Big, nice, big telescope. Why some telescopes are found on the surface of the Earth and some cannot be found on the surface. They're either high altitude, fly them in a plane, or they have to be in space, right? Why is that?
Because of
The atmosphere absorbs some of the colors of light. Okay. Now, actually, there are telescopes located in dry areas at the tops of mountains, right? Mauna Kea in Hawaii, or the Atacama Desert in Peru. Forgot the name of the telescope. It doesn't matter. But anyway, there are telescopes that are placed there. Why would that be helpful? Higher. What does that mean? Closer to space, right? There's less atmosphere to absorb the light, right? Drier. Why is drier important? There's less chance of having clouds, right? And then there's less stuff to absorb again. Explain why radio telescopes are found as part of an array, mostly found as a part of an array.
Because it can work as one big.
They act like one big telescope. Yeah, bigger is better, right? The bigger the telescope, the better the resolution will be. So having them in an array makes them act like one giant one. Okay, the order of colors, memorize. Okay, we're almost done with chapter 4. Well, this is a lot. Good luck to all the people who don't come here. Okay, you guys are here. Hopefully this will help you. The order of the colors. Okay, we went through that again. Radio, microwave, infrared. That's before you get to visible, right? Then in the visible, Roy G. Biv. Then above the visible, ultraviolet,
red is 700.
700 to 400, right? So what's green? About 550, right? Right.
Do we need to know the exact numbers, the colors?
Just roughly. Yeah, I put them in there. I guess I kind of wanted them. But it's not like I'm going to ask you any real detailed questions. But if I told you that there's a light, let's say I tell you that there's a color of light. I'm sorry, there's a light with a wavelength of 450 nanometers. Can you see it?
No.
Can you see it? 450 nanometers.
Yes.
Can you see it?
You should be able.
Yes, you can, because it's between 400 and 700 nanometers. Could you guess what color it is?
Indigo?
Indigo is a good guess. Some shade of blue or indigo is a good guess. That's a really good guess. You don't have to do much. I mean, that's like already kind of crazy. Okay, don't worry too much. All right, should we jump to chapter 3? Okay, we're going backwards. Chapter 3. Oh, good. Okay, we did cover all this stuff, so hopefully it's easier. Okay, chapter 3, Kepler's laws. Okay, let's see if we remember Kepler's laws. Law number 1. Planets orbit on elliptical paths, ellipses. What are some of the ideas about ellipses? Well, it has 2 foci. Instead of a single center, it's stretched out. There's 2 foci. There's a major axis, which is the longer axis, and a minor axis, which is the shorter axis, right? Just how far off is the ellipse, either the long way or the short way. The semi-major axis is exactly half of the long axis, right? Semi-major axis. What does eccentricity mean? Remember that word? How
wide, or the stretch of the.
how stretched out it is, right? Remember what a circle is? A perfect circle. What's the eccentricity? Zero. That's easy to remember. Circle, right? Circle. Eccentricity is 0. So the higher the eccentricity, what? The more stretched out it is. But it doesn't get to be very big. It's a number between 0 and 1. Okay, so it's not a big number. But the bigger that number is, the more stretched out it is. Okay. I think I forgot to talk about this. I meant to. Sorry about that. It's here in the study guide, thankfully. Because then you saw it, you're like, I don't know what that is. Oh, good thing. It's not fun. Okay. Conservation of angular momentum. So remember we talked a few minutes ago about conservation of energy? Well, we have also this idea of conservation of angular momentum. Angular momentum cannot be created or destroyed, right? Only transformed from, whatever, change somehow. Anyways, how does that work? You might remember that, I didn't finish Kepler's law. Sorry, I forgot. Let me go back, because it's actually related to the second law. Okay, are you ready? The second law states what? A planet sweeps out equal areas in equal times. I talked about pizza, right? If you're on one side of the ellipse, you get a nice squat wide slice, and if you're on the other side, you get a skinny long slice, right? What was the meaning of this Kepler second law? What was the meaning? What's the important idea? What's the more crust or less crust? Anybody remember what that means?
Just the time.
Greater distance, not greater time. Same time. Same time. Greater distance.
Oh, okay. So there's
Greater distance, same amount of time.
You get close to the sun, you go faster.
Okay, the speed, right? When you're close to the sun, you go faster. What's the word close to the sun? Perihelion, right? When you're closest to the sun, you move the fastest. When you're furthest from the sun, you move slowest actually, right? So this is actually called conservation of angular momentum. So again, this is not an equation class, but when you talk about angular momentum, there are 3 factors: the mass, the velocity, and the distance from the sun, n, v, and r. Okay? So this is constant. I want you to stop and think for a second. What does that mean? It's not getting bigger, it's not getting smaller. But when the object moves on an elliptical path, doesn't the r, or distance from the sun, get smaller? Doesn't it get smaller? Yeah. But what has to compensate for that? When this gets smaller, when r gets smaller, what happens? V gets bigger, right? And then the whole factor stays the same. It's called conservation of angular momentum. There's another way to learn about it that we're going to study in the future. It has to do with ice skating. Anybody seen ice skating before? They do this thing, pretty cool, where they have their arms out at the side and then they start their spin, right? They start their spin. And then what do? They pull their arms in, and what happens to the spin? They whip around, right? That is called conservation of angular momentum. So we'll study that a little bit later, but it turns out it's angular momentum that makes them spin faster. They can't change their angular momentum, but when they make themselves more compact, they have to spin faster as a result of that.
Does that mean stretching out their arms and slowing down?
That's correct, it does, and I can show you that, and we will see that, yeah.
So when the size increases, the speed increases.
Yes. So when the size decreases, the speed increases. The same thing's true when the object is moving around the sun. When it's close to the sun, r is small. The speed goes up to compensate. Okay. So that's the idea. It's in the book if you want to go and read that. I'm not going to deal with it very much. It's a little more complicated. So not worry about it. Yeah, probably you won't have to worry about it. Orbital period. What's that mean? Oh, the third law. Third law. That's the tricky one. What's the third law? P squared equals R cubed, right? That's the formula. P squared equals R cubed. Actually, I have it a little bit later in the study guide to remind you that you really do have to do this. Right? P squared equals R cubed. You're gonna have to do 1 or 2 problems, right? Don't be afraid, it's not that hard, but you know, I gave you some examples. I either give you P or I give you R, one or the other. If I give you P, what do you have to do? Find R. If I give you R, what do you have to do? Find P, right? You gotta find one or the other. And you won't need to do exact numbers. It's more like, can you get the right rough number, rough answer? But would you like to do a practice? Want to do a practice? What do you want to do? Okay, practice? You guys want? There aren't that many good practice ones. So if I practice enough, one of these is the one that's on the test. You get the idea? There aren't that many, okay? I think I've already done most of them. But anyway, let me see if I can throw a couple more. So let me see, I give you, okay, I haven't done this one with you. Let's say I give you R is 3 astronomical units, right? What am I looking for? What am I looking for? The 3? I'm looking for P, right? I want to know P, okay? So what's the formula? P squared equals R cubed. Okay, so what do I need this number? 3. I need to times itself and times itself again. 3 times 3. 9 times 3. 27. So P squared equals 27. Now don't be freaky on me. Just try to give me a rough number, right? What number is P pretty close to? 5. 5. Are we good? 5 times 5 is? 25. That's close, right? 6 times 6 is? That's way too big, right? So it's pretty close to 5, right? So the period is going to be, 5.1. I don't know, maybe 0.1, 5.1 something. I don't care, right? I just know it's close to 5, right? Close to 5 years is the right answer. You guys follow? It's not going to be that hard, all right? What's that? The other tricky one that I can give you is suppose these ones are harder to find good examples for. But suppose I gave you the period was 8 years, right? I did that with you already in class, but it's the best one I can think of. So if I give you that one, that's probably the one, right? What happens? P squared, 8 squared equals R cubed. That's right. I already heard the answer. The number is 4. 4 times 4 is 16, times 4 is 64. 8 times 8 is 64. So it's got to be something like that. You want to do one more? One more. We do one more item. What did I do? It's hard to come up with good ones. 3. How about 3? P equals 3 years. 3 years. Right? What's the R? 9. Wait, 9 is 27. Oh no, yeah. What is it? 27. No. P squared 9 equals R cubed. What number times itself times itself? A little more than what? 2, right? 2 times 2 is 4, times 2 is 8. That's pretty close. It's a little more than 2. I don't know what it is. 2.2. I don't know. R is like 2.2 astronomical units. Okay? I mean, I'm giving you more than you need. Okay? Don't go crazy. Those are a couple of examples. You see how it works. Try to find the closest answer that works. You can check all the answers, right? Just check the answers. Does it work or not? And if it doesn't work, throw it away, right? Take the good answers. Okay. Let's see. Orbital period. What's that mean? It's the time around the sun. The time it takes to make one revolution, right? One orbit, right? It could be, we're talking about the Earth. What's the orbital period of the Earth around the sun? 1 year. Or it could be the moon, right? All right, so now let's see if you remember. There's actually 2 ways to talk about the orbital period of the moon. One of them is in terms of the phases of the moon, and the other is the actual time it takes to orbit the moon. Do you remember the difference? So it's coming up, it's called, oh no, it's in the last, never mind, sorry, it's not in this chapter. Okay, but you remember the numbers? Yeah.
Phases is 23.5 and the actual rotation is 29.5.
Okay, so you got it backwards. The actual time is 27.3 days, but the phases time for full moon and full moon is 29.5 days. Okay, it's called the sidereal month and the synodic month, right? So the month. Okay. Galilean moons. Who remembers the 4 Galilean moons? You need to know by name. What are they called? Io, Europa, Ganymede, Callisto. Okay, those are the 4 Galilean moons. You should at least recognize them. Io is the closest. Ganymede is the largest. It's the largest one in the solar system. We're going to learn more about them. Mass, what's mass? The amount of stuff, right? How does that compare to force? What's a force that's associated with a mass? Anybody remember? It's like the force of gravity is called your weight, right? Your weight. So mass and weight, right? Weight is the force of gravity on a mass. More mass, more weight, right? What is a force? What is a force?
Push
A push or a pull. That's it. There's a push or there's a pull. And what does a force cause? What does a force cause? A mass to do something. What is it called? Accelerate. Accelerate. Causes a mass to accelerate. What does accelerate mean? By the way, I should have spent a little more time doing this, but I was kind of in a hurry. There's actually more than one way to accelerate. What does accelerate mean? See, most people who don't take science don't know what I'm talking about, but you guys will know. How do you accelerate? What does it mean? Change your velocity is the best answer. Okay. How about, can you change your speed and accelerate? Can you speed up? Does that accelerate? Yes. Can you slow down? Does that accelerate? Speed up or slow down is still called accelerate. Changing your speed, right? But what's the other way to change your velocity? Change your direction, right? So you change your speed, change your direction, or change both of them. And then you have accelerating, okay? Velocity, what's velocity again? Velocity?
Oh, speed.
Speed, and which direction you're moving with that speed, okay? What is speed? Oh, I guess we better define speed. How fast you're covering distance. It's distance divided by time, right? So it's miles per hour or meters per second. It's how quickly you cover distance. That's your speed, right? So you look at your speedometer on your car, it's measuring the speed, right? What's acceleration? We just said divided by the change in time. It's your velocity is changing. Okay, velocity changing. What's a vector? An arrow, right? It has 2 parts. What are the 2 parts called? The length or magnitude is called, and the direction. How long it is, and which way is it pointed, right? So which one of these things is a vector? So let me see if I meant to go through that with you. I kind of forgot. Which of the things that I've just listed are vectors? Is mass a vector? No. No, mass is not a vector. Why not? It doesn't have a direction. It's just mass, right? Does force have a direction? Is force a vector? Yes, force is a vector. How hard do you push or pull, and which way do you push or pull, right? It's a vector. Is velocity a vector? Yes. Yes, velocity is a vector. Is speed a vector? No, it is not. It's just how fast are you moving, right? So 50 miles an hour doesn't tell me which way I'm going. Speed is not a vector. And acceleration, is it a vector? Yes, acceleration is a vector. Okay. So you guys are doing the review. Can I just do one quick little thing, right? The vector is kind of important. So remember the equation. F equals ma, right? That's a pretty important equation. It's Newton's which law? That's the second law. You need to know it by number. That's Newton's second law of the equation. So if I don't want to introduce new stuff, but it's kind of fast. If I put a little arrow over it, guess what that means? That thing is a vector, right? A little arrow. And this thing over here is a vector. Is this thing a vector? No, this is not a vector. Okay? So I got a vector over here, I got a vector over here. What does the vector mean? It has a magnitude, it has a direction. But only this and this are vectors. What does it mean? If they're on both sides of the equal, there's only one vector here and there's only one vector here. They have to be pointed in the same direction, right? If you push on something with a force in this direction, which way will it accelerate? In this direction, right? Hopefully that makes sense. You push on it that way, that's the way that it accelerates. Push on it that way, that's the way that it accelerates. Does that make sense? Yeah. The force and the acceleration are always pointed in the same direction. All right. Anyway, yeah, that's you don't need all that. Newton's laws of motion. Okay, let's see. Let's go through them. Number one, this car surfer was my first example. Law number one. The law of inertia. An object at rest remains at rest. An object that's moving continues moving with a constant velocity unless a force acts on it. Okay? And so something that's moving already wants to keep going. They go flying off the front of the car. That was the example that I gave. Or the one where the guy steps on the gas and the friend is on the top of the roof. They just don't go anywhere. They fall off. So law of inertia, number one. Law number two, F equals ma. Law number three. So what's the words, by the way? A force
law
causes a mass to accelerate. That's the words that go with that equation. F equals ma. Yes? The fire extinguisher is all three. So let's go through that again. We'll do that again. The fire extinguisher is all three. Why? Because the way it works is the fire extinguisher pushes gases out the back. And what do the gases do? They push back on the fire extinguisher, which I happen to be sitting on, right, at the cart, the fire extinguisher. So the gases are going to exert a force according to which law? If the fire extinguisher pushes backwards on the gases push forward on the fire extinguisher. That's the third law, right? So that's how the third law comes in. The force of the gases pushing on the cart and me causes the mass to accelerate. That's the second law. And the third law, if I didn't do anything, I would sit still. But as soon as I pressed the handle, I started to move. That's actually the law of inertia. I'll stay at rest if nothing is acting on me. But as soon as the force acts on you, then I'm going to start changing my motion. So it's really the first law too. Okay? That good?
Yeah.
Kind of all three. What's the first law? The first law, the law of inertia. An object at rest will stay at rest or remain at rest. But an object that's moving already will keep moving with a constant velocity unless a force acts on it. Okay? They'll just keep going forever. Why do things slow down and stop when you slide them on the ground? Aristotle said because they want to be stopped, but that's not right. Newton said because there's a force of friction slowing it down. There has to be a force constant.
What's the name of the third law?
I call it law of action, reaction. For every force, there's an equal but opposite reaction force. So I don't move myself, remember? I push back on the floor, and the floor pushes forward onto me. That's how I move, right? But I'm not making myself move. Okay, universal law of gravity. That was the equation. Big G, big M, little m, big M, M1, 2, M1, M2 over D squared, right? That was the equation that we wrote down. Let's see if I can find that. I just write it on the board. For the people at home, there's our formula. There it is, right there. That's the one. Okay. F, the force of gravity, equals big G. We don't worry about the big G in this class, right? We don't use it. But the formula has M and M on the top and D squared on the bottom. Those are the factors you need to understand. So what makes attraction between two objects? They have to have mass, and they have to be some distance from each other. If the distance is infinity, they don't feel anything. But infinity you can't get to anyway, so don't worry about it. Okay, so what happens is, I have a situation where there's two objects attracting each other. And then I can ask a question like this. What would happen to the force of attraction if one of the objects was twice as much mass as it originally was? What would happen to the force? So if you make one of the masses 2 times as big, what will happen to my answer? It'll be 2 times as big. What if both of the masses were twice as big as they were originally? What will happen then? You get 4 times attraction. Okay? What happens if you change the distance, right? What if the distance gets bigger? Does the force of gravity get stronger or weaker? The bigger the number, weaker force, right? Inversely proportional to the distance squared. And so the numbers you want to think about, what happens if I double the distance, right? We did that example with the ladder. If you double the distance, what happens when you square it? What does it become? It becomes a 4 in the denominator. So you have to divide by 4. What if you tripled the distance? What would you be dividing by? 3 squared, or 9. You have to divide by 9. You do 4 times the distance. Divide by 4 times 4 is 16, right? So whatever the factor, you have to figure out how much further did I go? Did I go twice as far, 3 times as far, 5 times as far, 10 times as far, right? How much further did I go? And then because it's squared, that factor gets squared as well. So 5 times as far would be 1 over 5 squared, or 1/25 as much force of attraction. Okay. What about this? Sorry, throw it out there. What if you get closer together? What happens to the force of gravity? It gets stronger, right? So I'm gonna just, for everybody at home, I'm gonna do one quick example here, okay? Because it's tricky. Most people get it wrong, but you should be able to do it. Let's see if this is gonna work, right? What happens if I go half the distance, or I make the distance between them half as big? What happens to the strength of the force of gravity, right? So F equals big G, I don't care, M1, M2, I don't care, but this is the part that's changing. I have 1/2 the distance squared. What's the strength of gravity? Stronger or weaker? Stronger, because they're closer together. How much stronger? Not supposed to be that hard, but a lot of times people get confused. What's 1/2 of 1/2? A quarter. So you have to divide by a quarter. Who knows how to divide by a quarter? Okay, not sure. Okay, so G, M1, M2 divided by 1/4 G squared. What's the trick? When you divide by a fraction, it's the same thing as multiplying by what? The reciprocal. Okay? Dividing by 1/4 is actually the same as multiplying by 4. So when you shrink the distance to only half as much, you get 4 times as strong a force of attraction. Does that make sense? You got that? Okay. So closer, force gets stronger. Further, the force gets weaker according to distance squared. All right, so that's a little tricky. So I did it for you. Hopefully you understand it. Okay.
Because when it's times 16th, it's 1/16 of the power, right?
If you go how far?
When you said like
1/4 maybe.
Or remember we did like the times 16, but that's 1/16.
I'm not sure we're talking about. Did we do 16? I don't remember 16. 4 times as far? 4 times as far, maybe. Then it would be 1/16. Yeah. The original. So we do 16. Okay. How am I going to get 2 more chapters done? Woo, guys are not a lot. Okay. What is the weight? The weight is the force of gravity. Weight is the force of gravity. Oh, you can't see that. Weight is the force of gravity. What's centripetal force? Okay, we only covered this just today, right? If something is moving in a circle, what does it mean? Is the force in the same direction as the velocity, the opposite, or to the side? It's to the side. It's toward the center of the circle. It's making it turn around a circle, right? Centripetal acceleration is the acceleration caused by the centripetal force. I wouldn't worry about that. Escape velocity, you should know that though. What does it mean?
Is that when it's going too fast that it will just?
Yeah, it's the speed needed to get away from an object. So the stronger the gravity is, the harder it is to get away, the greater the escape velocity would be. Right? That's the basic idea. So I want to give you some hypothetical situations. Imagine we go to a planet that has the same mass as Earth, but it's a little bit larger. Right? It's somehow made of stuff that makes it a little bit larger. Would the gravity on that planet be stronger or weaker than the gravity on the Earth? It's the same mass, but a little bit larger in size. What would happen to the force of gravity? Stronger or weaker? That was supposed to be easier. What's the answer? A little bit less, right? Because you're further away from the center of the planet. The gravity on that planet would be a little bit weaker. So what would it mean about the escape velocity? Would it be easier or harder to get away from that planet? Easier. It would be easier. The escape velocity would be smaller. Okay? That's the kind of thing. How about you go to the moon, right? The moon has a much weaker gravity. Is the escape velocity of the moon the same as the one for Earth? No. No, not even close. Is it a lot more or a lot less? It's a lot less. The smaller the gravity, the easier it is to get away. It's the velocity needed to get away. We can do calculations, but we can. Okay, all right. Explain why Copernicus's heliocentric model could explain retrograde motion, or how did it explain retrograde motion, and why is it superior to the geocentric model? So what did Copernicus say? The sun is in the middle, and the planets go around, and the closer you are to the sun, do they move faster or slower? Faster. They move faster. The further away you get from the sun, the slower the planets go around. Copernicus, by the way, said that they were perfect circles. Keep that in mind. That's not right. Okay, remember there are ellipses a little bit. Okay, so but how did he explain retrograde motion? Why do you see a planet going retrograde?
Oh, because it's a catch and pass.
You're passing it or it's passing you. Okay, it's the relative velocity of the two planets to each other. Okay, why is this better than the Ptolemaic model, which is geocentric? Why is it better? Is it more or less complicated? Which one?
Less complicated.
It's a lot less complicated. Ptolemy's model had these circles called deferents, and then little tiny circles on top of that called epicycles. It was confusing. Why did they do that? He had no explanation. It doesn't make it's really confusing why the planet would want to do that. But it worked pretty well. Not perfectly, but pretty well. Better than back to the Copernicus model for a while. But it still was a more complex model, and so we prefer the easy, simple model instead. How did Tycho Brahe make a big contribution? What was his big contribution? He was the big observer, the data collector. He built this beautiful 3-story tall astrolabe, which measured the positions of the stars and planets, collected data for 25 years or so, right? Who used his data to make something productive? Kepler, Johannes Kepler, right? Kepler's third law, we already went through the practice of p squared equals r cubed. What are the major discoveries of Galileo? I already listed them here, but what did he discover about the moon? Is it perfect? No. No, it's imperfect. It has mountains and valleys and craters. It's not perfect. It's not the Greek idea of perfection. How about sunspots? Again, the sun is supposed to be perfect, but there's spots on it. Spots are not perfection. How about the phases of Venus, right? What does that tell you? Venus goes around the sun, right? It's the geometry of its position relative to us that gives us the phase. Just like when the moon goes around us, we get a different geometry with the sun and the earth, okay? So that was the only way to see it. By the way, I should mention something that I think is on the test. Those of you listening at home, heads up. Which planets are closest to the sun? And I'm sorry, which planets display phases? I did talk about that, right? Which one are they?
Are they the 5 closest?
Mercury and Venus. That's it. Nobody else. What is the phase going to be when you look at Jupiter, Saturn, or Mars? Full. Why? When do you see Jupiter, Saturn, or Mars? When it's nighttime. When you're looking away from the sun, it's full. Okay? On the other hand, Venus and Mercury are closer to the sun. We can see phases. So what time of the day or night are Mercury and Venus visible? This is a new thing. I don't think I went over this in class, but you need to know it. Are they visible in the middle of the night, Venus and Mercury? Yes or no? Not at all. Never. Venus and Mercury cannot be seen in the middle of the night. Why? Because they're close to the sun. Mercury and Venus are close to the sun. So what time do we see them? Just before dawn, morning stars, and just after sunset, evening stars, right? We only see them when they're near the sun. So which horizon would they be on if it's just before dawn? Which horizon could you see them? Where does the sun rise?
East.
In the east. Where would they be? In the east. In the east before dawn, or in the west after sunset. That's the only place you will ever see them. That's it, okay? Because they're closer to the sun. They have to be near the sun. Okay, blah, blah, blah. Like everything. Oh, the stars of Mercury and the moons of Jupiter, which are called the Galilean moons. Okay. Describe Galileo's discovery about mass and acceleration. What did he show? We saw just a little video clip about that. All objects fall with the same rate of acceleration, except there's a problem. What's the problem? There's air resistance. If you can take it away, they would all fall at the same rate. Okay, how does force cause mass to accelerate? I think I did that. Oh, so if the force is with the velocity, what happens to you? You speed up, right? If the force is against your velocity, what happens? Slow down. You slow down. The force is to the side, what do? Change direction. You turn, right? And you turn, causes you to turn. And those are the three ways. Let's see. How does the strength? I did this already. And I did this too. Okay, well, kind of, right? What happens if you have the same size planet but more mass? As would it be stronger or weaker gravity? What do you think? Stronger. Stronger gravity would be higher or lower escape velocity. Lower. The stronger the gravity, the higher the escape velocity would need to be. Okay, so that's the thing to do. Memorize the order of the planets. Ooh, you all know the order. First planet, Mercury. Second planet, Venus. Third planet, Earth. Fourth planet, Mars. Fifth planet, Jupiter. The last three spell out the word sun. So Saturn, Uranus, and Neptune. We're not worried about Uranus and Neptune right now, but they will be important. Do you know the days of the week associated with the day, the planets and the moons, right? Sunday,
Monday's the
Moon Day,
Tuesday's
Mars days, Miércoles, Mercury Day, Jueves, Jove Day or Jupiter Day,
Friday.
Viernes, Venus Day, and Saturn Day, right? Okay, those are the 7 days of the week. Okay, blah, 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 blah. I got that, right? Got it all? Okay, 2. Gotta keep going, right? Keep going. Use our time here. Oh my gosh, there's so many words. I don't know if we can finish this in 2 hours.
We can choose number
I
one.
think I can.
We have 10 minutes.
Why don't you just forget about the definition?
Just skip the definitions, jump down. Okay, you guys take care of the definitions. All right, anybody have any question on the definitions? That's a great idea. Thank you for your suggestion. Okay, so we'll jump down, chapter 2. Lots of definitions. Describe the reason for the season. Okay, let's start with that one. What's the reason for the season? The tilt of the earth, right? The reason for the seasons is the tilt of the earth. So what happens as a result of the tilt of the earth is that the sun will take a different path through the sky, right? In the summertime, what does the sun do? Take a high path or a low path? Takes a high path. So there's 2 things that happen as a result of that. Number 1, the sunlight is more directly pointing down at the earth. What happened? Higher intensity. The light is more intense, right? And then the second thing is it's taking a higher path. It's a bigger path, right? A longer path. So that are longer, right? So sun, we have longer days with more intense light. That's summertime. Winter is the opposite. Okay? What about the equinox? What happens then? Equinox.
Equal day.
Day and night are equal. 12 hours of day, 12 hours of night. Okay, determine the rising time, crossing of the meridian, and the setting time for any given phase of the moon. The way that I memorize it, I memorize 4, and then I figure out the ones in between. The 4 that I memorize are the new moon. The new moon is highest at noon when the sun is highest, because it's lined up with the sun. The new moon is highest at noon. The first quarter moon is highest at sunset. The full moon is highest at midnight. And the third quarter moon is highest at sunrise. I can do anything from that. If you want, ask a question, but that's what I do. I memorize the facts that I just told you, and everything else I can figure it out.
That one more time.
One more time. The new moon, which follows the sun, right, is lined up with the sun, is highest at noon. The first quarter moon, which is exactly halfway lit up on the west side, on the right-hand side, is highest at sunset. The full moon is highest at midnight. The third quarter moon is highest at sunrise, and that's when the left-hand side or the east side is lit up. Okay? And from everything else you can figure it out. Okay? When does the waxing crescent come? In between what two phases?
Waxing crescent.
Waxing crescent between the new and the first quarter. What about a waning gibbous? When is that? Between full and third quarter, right? What about waning crescent? Third quarter and new, right? What about waxing gibbous?
Between
First quarter and full, right? Okay, you know where they go, and then you can figure that out, okay? Blah, 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 blah. Determine the geometry of the eclipse. So remember that eclipses only happen once in a while. There's actually eclipse seasons that happen about every 6 months, okay? That's when the nodes are in the right phase, right? What's a node? When the moon is passing in its orbit, when it passes through the ecliptic plane, we call it a node. How many nodes per month? 2, one going up, one coming back down. And then it has to be the right phase, either a new or a full moon. If it's a new moon, what kind of eclipse will you have? If it's an eclipse and you have a new moon, it will be a solar eclipse. If it's a full moon, it will be a lunar eclipse. New moon and solar eclipse, how long do they last? A few minutes, right? A few minutes. What's the longest one? Like 7.5 minutes, okay? How about the lunar eclipse? How long do they last? 2 hours, right? A couple of hours is typical. Okay, describe the condition. Oh, I just gave you that, right? How do you get, what's the longest solar eclipse? What's the longest solar eclipse? How do you get that? Big moon or small moon? Which one? Big moon. And big sun or small sun? Small sun, right? Then you can block it for the longest amount of time. How do you get a big moon? Where is the moon in its orbit? Not apogee, because then it would be small, right? How do you get the big moon? Perigee, right? When you're at perigee. Perigee means that the moon is closest to G, which is geo, meaning Earth. The moon is closest to the Earth, big. What makes the sun small? The Earth is going around the sun, and is it close or far? Aphelion, furthest from the sun. That's the perfect conditions for the longest eclipse. Okay, it doesn't happen very often. Okay, really rare. Why did Aristotle believe geocentric was right? One big idea. He couldn't see, right? Stellar parallax. He couldn't see it. And as a result, he was smart. He's a smart guy, right? He said the Earth isn't moving. If I can't see the stars moving, the Earth is not moving. What about Ptolemy's geocentric model, right? What is everything going around in Ptolemy's model? The Earth. It's the Earth at the center, geocentric. And the main circles are called deferents, and the little circles are called epicycles, just names, right? The angular size of the sun or the moon, right? That's the size in degrees. It's about 1/2 degree. They're about the same, which is why you can have an eclipse, right? That's cool. It's also the size of your pinky held out, right? You guys know that? Okay. What are the dates of the seasons? 321, 621, 921, 1221. So you should know what that season is called. Everybody remember? It's pretty easy, okay. And is it the same for the southern hemisphere? Nope. Flip, right? Reverse. Blah, 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 blah. Axial tilt of the Earth, 23.5 degrees. What about this one? Precession of the Earth. I don't know that I talked about that in class, but Phil talked about it, and the book talked about it.
I brought it up.
You did bring it up. Yeah, there's a wobble. So the Earth right now is pointed at Polaris, but it hasn't always pointed at Polaris. And it takes a 26,000-year wobble to point back at Polaris. So it turns out in a few thousand years, it won't be pointed at Polaris anymore. But it'll come back again after about 26,500 years, okay? Again, not a big deal. You know the phase of the moon. Sidereal means the time it takes for the moon to go once around the Earth, 360 degrees. Synodic is from full moon to full moon, right? The full period. is the week we did that, okay? We do chapter 1 last year. Okay? I'm skipping the definition, no, we're doing it. It's much faster. A lot of stuff though. Okay, change between ordinary and scientific notation. Everybody good? You want to review or you got it? Simple questions, not difficult.
What was the ordinary?
What's ordinary?
Yes, the long number.
Yeah, big long number. Turn it into scientific notation. You want to do one quick example? I mean, they're not that hard. You want to?
You know the small angle formula?
Oh yeah, small angle formula. Okay, the small angular formula is something that's in the book, and it says this. Ready? It's very tiny little idea, but it's an important idea. And again, we don't do formulas in our class, so why do I want you to even think about this? If I have an object that has some size right here, right? Big V is the size, and let's put little d as the distance, okay? It turns out that the angle that I can see it made is related to these two numbers. If the angle is small, this angle is equal to this divided by this. So what does it mean? If this is bigger, you get a bigger angle. But if this is bigger, what happens? The further away the object is, the smaller the angle will be. That's it. That's called the small angle formula. And if anybody knows radians, you have to use radians to make this work. We're not doing any of that. Okay? If it's a bigger object, it'll have a bigger angle. If it's further away, it'll have a smaller angle. That's it. Okay? That's the key idea. Order of magnitude, what does that mean? The closest, power of 10, right? So just for your information, number 5 and above, you round up, right? So 5.01 times 10 to the 8th. What's the order of magnitude? 5.01. Doesn't matter how much more than 5. It's above 5. What do? You go up 1 more power. So that's 10 to the 9th. That's 10 to the 9th. 5.01 times 10 to the 8th, round it up. If it's 4.999 times 10 to the 3rd, kilometers per second, right? What does that become? What's the order of magnitude? It's 10 to the 3rd. It doesn't go up, right? You just round it to the nearest power of 10. Okay. So actually, if the number is written in scientific notation, you do have to look at this number just in case. Okay? I have to run that. Okay. Organized by size. What's the smallest thing there? A subatomic particle. What does that mean? Proton, neutron, electron. Are they bigger or smaller than an atom? They're smaller. They're parts of an atom, right? That would be the smallest thing. And then you have an atom, and then dust, single sort of organism, planet, star, planetary system, galaxy, galaxy cluster, galaxy supercluster, and the universe. Right? Everything. So you should know them in order, right? Do you need to know the order of magnitude? No, that's a little too much. But if I give you 2 orders of magnitude, you should be able to compare them to each other. How much bigger is a planet, 10 to the 6th, right? A typical planet than this room, right? How big is this room? How big is this room? Is it closer to 1 meter, 10 to the 0, or 10 meters, 10 to the 1st? 10 to the 1st. It's pretty close to 10 to the 1st, right? How much bigger is the Earth than this room? 5 orders. 5 orders of magnitude. 100,000 times as big as this room. Okay? That's the order of magnitude. 10 to the 1, 10 to the 6th, 5 orders of magnitude, 10 to the 5th. Right? Got it? Sort of? Okay. What's the steps of the scientific method? Step 1.
Observation.
Observation, right? See something, see a problem, or ask a question, right? What is that? How's that work, right? Number 2, hypothesis. Create a hypothesis that gives you your best. It's not just a guess, it's an educated, best thing that you can do, right? It's based on all the information you have. Then step 3, experiment. And step 4, data. Evaluate your experiment, confirm or refute, right? One or the other. And then what do? You give up? Never give up. Even if it's wrong, what do? Go back to the drawing board, try again. Create a new hypothesis, try it again, okay? Size of the Earth, everybody remember that? 6,400 kilometers in radius, 4,000 miles. The diameter is twice that, right? There is a question where you have to show me you memorize these numbers. Size of the moon, 1/4, 25% of the Earth, right? Order of magnitude between the sun and the Earth is about 100 times as big, right? Okay. All right. Well, we finished. Good job. Good job. Did that help? Yes. Yeah. Okay. Good luck tomorrow. Don't be nervous. Get some sleep. Bring a pencil. All right. So thank you, ladies and gentlemen, in the streaming audience. Okay, we're going to close this out, and you'll be able to look at the recording. Okay. So thank you very much. Hopefully you got something out of that too.